Hi there and welcome to PhD at Living. It's time for episode 4 of our beer series, and it's a topic I've teased about a couple times, but now we're gonna get into that magical, mystical, 0 IBU IPA. My wife and I were on vacation in Denver visiting one of my best friends, and we went to one of the, roughly 8,000 local breweries in Denver and had some beers. There was one on the menu that was a 0 IBU IPA, and Devin Brain went off and said, IPA? 0 IBU? Nah. But yes, says science. Let's see what we're talking about. 1 IBU, or International Bitterness Unit, is defined as 1 part per million isohumulone in beer. For those of you sticklers out there, it's not just isohumulone that contributes to the IBU. In fact, if you add 1 ppm isohumulone, the IBU goes up about 0.7. It's a rabbit hole. I don't want to go down there. If you want to talk about it, get your own channel. Thanks. What's isohumulone, you ask? Great question, but the answer has to go back to regular humulone. Let's do it! Humulone, seen here and mentioned in our previous video, is one of the compounds responsible for bitterness in beer. It's called an alpha acid, but as we know, there is no carboxylic functionality on here, so that's a dumb name and we're not going to say it. It's technically more correctly an acylone, meaning it's an alpha hydroxy ketone. When exposed to hot temperatures, like for instance in the boil, yeah, the boil. Remember that from that video I did? If you haven't seen it, go back and watch it. What are you doing? Humulone isomerizes, meaning the structure of the molecule changes, but all of the atoms are retained. It goes from a 6-membered ring with 2 double bonds to a 5-membered ring with 1 double bond. If you count up all the atoms, you can see that we aren't adding any or taking any away, meaning the humulone and the isohumulone have the same molecular formula, C21H30O5, and they're isomers. The actual arrow pushing mechanism for this is fairly complicated, so I'm not going to go through it in detail, but I will hit the highlights. The bulk of the isomerization goes through something called an acylone rearrangement. And hey, we have these acylone groups on humulone. If I number the carbons in both the 6-membered ring of the humulone and the 5-membered ring of the isohumulone, we can start to see things that happen here. Namely, the 1, 2, and 3 positions in both the humulone and the isohumulone stay the same. The real fun happens in the 4, 5, and 6 position. First, the hydroxy group on the 5 position of the 6-membered ring moves to the 4 position of the 5-membered ring. And the prenyl group that was on the 4 position of the 6-membered ring moves to the 5 position of the 5-membered ring. And we have the carbon on 6 in the humulone and the hydroxy in the prenyl group here collapsing entirely and moving to the 4 position of the 5-membered ring. Finally, we have the hydroxy that was here on 6 moving completely out of the ring structure in isohumulone and being oxidized into a ketone, giving us isohumulone. Damn, I'm good! Side note here, the paper I read describing this process of finding the actual crystal structure here was using X-ray diffraction in order to get it. And there was one sentence in there that was particularly near and dear to my heart. Empirically, the vast number of useful salt combinations was greatly reduced by the inability to grow X-ray quality crystals. In order to get an X-ray quality crystal, you have to grow a very, very fine crystal with no obvious imperfections or defects. In the understatement of my life, that is easier said than done. I spent 2 years trying to grow crystals of X-ray quality and couldn't do it. I tried different solvents. I tried combinations of solvents. I tried heating them. I tried freezing them. I tried seeding them. I tried everything. Growing X-ray quality crystals is voodoo black magic, and anyone who tells you otherwise is lying. We've covered the structure and drawing of molecules, but we've never really hit what the wedges and dashes mean. It doesn't take a lot to think that a molecule is actually not 2-dimensional and has some 3-dimensional orientation to it, and those try to help us explain it in the 2-dimensional whiteboard arena. If you think the majority of the molecule is in the plane of the whiteboard, the wedge indicates that that group is coming straight out at you, while the dash means that group is going behind the plane of the whiteboard. This wiggle here on this prenyl group I've drawn very emphatically to say that it could be either one. It could come straight out at you or go back behind. It's in relation to this hydroxy group here that is also coming out. So if the prenyl group is coming out as well, it's called cis isohumulone, and if the group is going back behind the plane of the whiteboard, it's called trans isohumulone. Alright, now we know what cis and trans isohumulone look like, and that both of them are isomers of regular humulone. The next step is figuring out how much of them we have in the beer, and that takes some more chemistry. In order to find out how much isohumulone we have, we want to separate it from the rest of the beer. So first we slightly acidify it. So we take isohumulone, I'm going to abbreviate that IH, and we add some acid to it, probably something like hydrochloric acid. Because the isohumulone is already a little bit hydrophobic, meaning it doesn't like water that much, adding the acid makes it even more hydrophobic. Step 2 is an extraction of the isohumulones into isooctane, or 3,3,4-trimethylpentane for those of you playing at home. The purpose of this step is to take the acidified isohumulones and the other IBU contributing compounds in the wort and separate them out from the rest of it. So those acidified compounds go into the isooctane or organic layer, while the rest of everything else stays at home. The third step in our three-step process is analysis via UV vis, or ultraviolet visual spectroscopy. You can also use high-performance liquid chromatography, or HPLC, but it's significantly more expensive and much finickier. It's a word, shut up. The isohumulones have a good absorbance in the UV vis spectrum at about 275 nanometers, so it's as simple as plotting absorbance versus concentration in a standard curve, getting a bunch of different concentrations, known concentrations of your isohumulones, finding your unknown, getting the absorbance, and putting it right back down to the concentration, the parts per million of isohumulone in your beer, and IBU. Which brings us back to the question of the day and the 0 IBU IPA. Was it bitter? Hell yeah, it was horrible! I am admittedly not a hophead. In my defense, however, just because there are no isohumulones in the beer does not mean there isn't any perceived bitterness. So there. And that pretty much fills in the rest of the story. Just because you don't have isohumulones in the beer doesn't mean the beer is not going to be bitter or hoppy. All the other flavors from the hops are still going to be there. But Devin, how do we make sure we ain't going to get none of them isohumulones? Well, I sort of alluded to it earlier. The isomerization of humulone happens at elevated temperatures, so if you put your hops in after the boil, you'll get all of the flavors and characteristic aromas from the hops, but none of the bitterness from the isohumulones. Another great point is why the beta acids can't contribute to the IBU. They can't isomerize, and the reason they can't isomerize is because they don't have that alpha hydroxy in the acylone group that humulone does. The analog lupulone doesn't have it, it has another prene group on it, so it can't isomerize, it can't contribute. As a final note, humans really can't taste bitterness above about 100 to 150 IBU, so keep that in mind the next time you go for that 65,000 IBU quintuple IPA. And there you go, a 0 IBU IPA. I think I'll go have one. Not. See you later. And that, as much as anything, led to my drinking problem.